Hi, I am Karthik Rannan. I am the president of the Wall Street Club of Pilani Hyderabad campus. Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives while they try to navigate the world of finance. I am happy that we will be able to close this workshop successfully on a very good note.
Hi, I am Regularization and I am the technical director of the Wall Street Club at Pilani Hyderabad campus. It was a great amazing conducting this workshop with XLR. The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets, which was very helpful for the people who are interested in the field of finance, business or analytics in general. Thank you.
I attended a workshop conducted by CSA and ACM in collaboration with XLR. So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
The journey was great. Initially, I thought that I was not proficient enough in Excel, but later I came to know there was no prerequisites for it, and then I applied for it, and it was a great course, and it started from basics and took me to a great extent.
Good evening, myself Kavya Ganatra. I am from Computer Science Association. I was the POC for this ML workshop conducted by CSA and ACM in collaboration with XLR. The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our technical fest Atmos, and I thank XLR for being a part of it. Thank you.
hello everyone. My name is Tasneem. I'm the senior manager at 98 percentile in the HR department. And today we did a wonderful drive with XLR. It was amazing right from the very beginning, from the very first day when I got in touch with them till today. I think it was an extremely smooth journey with them. There were multiple follow-ups done by the representatives in order to check that we would be, what time we would be coming, how many people would be coming, what vehicle we would get. To that extent, they were so precise in giving all the information to us. It was extremely great to get associated with them and have a drive at XLR campus. So we are very, very happy that we got a chance to do this. Now, coming to the students, what XLR had, I think they were extremely enthusiastic. They were well prepared. They were aware of what they are coming for. I think there was some back end preparation which they did that was commendable. They also were very confident and they were open to any kind of thing we were asking them to do. That was I think the best part. Now, I really hope we have a very, very fruitful association with each one of them and XLR in future. We are really looking forward to have many more drives like this.
Hi everyone, my name is Prachi Sharma and I'm the Senior Project Manager for IT Department at 90th percentile. So today we were here for this IT bootcamp, right, this technical drive and at XLR. So it was a great experience and I would feel that the students, they are the freshers, right, but it doesn't seem like that. So if I talk about their technical and cognitive ability, they all seems pretty good in that and that's what I felt. And I guess they have been taught pretty well at XLR, so that's how they have performed good in their aptitude and the technical tests. So I wish them all the best and it was a very great experience over here.
Hi, this is Patan, Technology Consulting Manager from 98th percentile. We visited XLR for the campus placement drive and it went very well today. Miss Ambika, Miss Pragati
Afternoon, everyone. Hope I am audible. You guys are able to see my screen as well. So just give me a couple of confirmation, guys, and we can start then. Okay. Kirti Kumar, thank you. Ranganatha Raju sir, Vinod Babu sir, thank you. All right, guys. So I see still couple of people needs to join. I request everyone to join in fast. Okay, thanks for confirmation, sir. Whoso are not joined in, I request everyone to join in fast because we're going to start the session, and I'm going to cover very important topic, which is chain rule, and then followed by the topic which is called as exploding and vanishing gradient. And today we'll try to implement the architecture as well, right? So we'll try to see the two architectures, how we can implement this one. All right. So let's have a recap till the time people join in. So we started understanding like how the deep learning started, how it is made an efforts to make the copy of the human functionality. And then we know the three component input layer, hidden layer, output layer. This is the path which we discussed. This is the first model which was introduced, single neuron model in 1943, Michael and Pitts. And then they realized that they need to stack the neurons because single perceptron or single neuron out here will not be useful. So they created this kind of architecture which was called as multi-layer perceptron, right? And that's how the thing started. And then they initially introduced the activation function, then the two-step process which happens out here. This is what we were able to understand, what kind of a process happens and how the entire calculation happens inside the neuron, right? This is what we were able to see out here. And then when we were able to see this process, we understood that there at step 1 and step 2 happens, and activation function is playing a very important role out here, right, in order to perform this operation. And then we were able to go deep dive into the different activation function and the role of the activation function which are available out here, and which function works as well, right? How it is trying to perform the scaling, what kind of a job it does, how it bring the non-linearity to the equation, and how it is performing overall or in order to perform the prediction. That's what we have seen. And then we were able to understand that loss function is also playing a very important role. If it's a regression problem, then we'll using a different loss function. If it's a classification or multi-class, we are using the binary cross entropy or sparse cross entropy function, right? And how the actual calculation happens in terms of the classification when we're trying to predict the different classes. This is what we have seen. And then this is what the typical regression equation look like, right? Loss equation. And loss is, guys, try to understand there is a difference between loss and cost. So when we try to calculate the loss for the single data point, it's called as loss. And then when we try to calculate it for the entire data point, it will be caused as a cost function for the entire data set, right? Actual minus pretend. These are some of the loss functions which we can use: L1 loss, L2 loss, right? Huber loss and Hinge loss. And the very important topic which we learned, right, which makes this thing happening, or you can say it is a core or heart of the entire back propagation or entire neural network, due to which the machines and the AI learns, right? That is back propagation. And in order to perform the back propagation, the optimizers are playing a very important role, right? So we have seen the gradient descent, three flavors of gradient descent. Can anyone quickly tell me what all the three flavors we have seen for the gradient descent? Gradient descent algorithm, three flavors. And then we obviously discuss what is called as momentum, and with momentum how it will look like. Yeah, I am talking about the basic flavors, ma'am. Rashmi Lad, ma'am. Thank for the gradient descent. Yeah, gradient descent. Adam is there. That's true. Adaptive moments to estimation. So I'm talking what kind of a vanilla flavor, and we discuss one more flavor along with this one, right? So quickly, anyone, if you remember, and what is the difference? Yeah, mini batch, stochastic. Yeah, and vanilla flavor, right? And what is the difference, if anyone can tell me how they are differentiated from each other in terms of the equations, what kind of a data they are using? All right, let's see who answers this one. So what is the difference between vanilla, gradient descent, mini batch, and stochastic? Come on, guys. If you could recall yesterday's session. Yeah. So what is the difference? Let me write it here. We have our vanilla flavor here. Vanilla gradient descent, right? Then we have something called as mini batch, correct? Mini batch gradient descent. Then we have our stochastic gradient descent, right? This is the third one. So what is the difference, guys? Can anyone tell me? Still I am awaiting your responses. So what is the difference between all these three? Let me write my equation here. The objective of the entire artificial neural network will be y equal to wx plus b, where we are trying to find out this model parameter, right? So these are weights and biases. This is what we are trying to find out. Weights and biases, correct? And this is what optimizer does. They try to optimize or adjust the model parameters, correct? So that is the entire thing, and that's how the back propagation starts. All right, guys, if you are not able to recall, let me tell you. So what is the main difference out here? The main difference will be in vanilla gradient descent. We are using all the data points, right? We are using all the data points which are given to us in order to find out the model parameters, correct? All the data points are used when we try to perform this gradient descent algorithm, right? In order to perform this kind of operation in order to optimize the model parameters. So we are using all the data points. In mini batch, we are using in the batches, correct? So we are not taking entire data. In the batch wise manner, we are taking data and then we are trying to find out the model parameters W and B, right? And then we'll try to optimize them. And in the third one, in stochastic gradient descent, we are using single data point. And then we're trying to find out. And that's the reason. So sometimes when you're trying to use the stochastic gradient descent, it could have a large variance out here, right? So we want to make sure that it is trying to converge smoothly towards the core. That's the reason. So we are using it with momentum, right? So this is what we have discussed. Hope you are able to understand, correct? So let's go ahead then. And since we are having all the optimizer in hand now, and we have discussed that how to choose the optimizer, like I told you, the best optimizer will be something which is trying to deal with the momentum as well, right? So each and every equation we have something related to time, something related to the sequence of the data, right? And in order to perform that, we need to understand that. And stochastic gradient descent is used in many papers with momentum or without momentum, right? This is what the people have seen and seen. In deeper neural network, they are using Adam, obviously, right? This is what we have seen. In back propagation, exactly when we're trying to talk more detail about the back propagation, this is the way we are doing the forward propagation, right? Forward propagation. And forward propagation is machine learning. Anything, guys? Can anyone tell me when the actual learning happening, whether it is happening in the forward propagation? This is one of the favorite question which interviewers ask. When the learning happens, or when the optimal values of the weights and biases are find out, in which process? We have something called as forward propagation. We have something called as back propagation, right? So in which propagation model actually starts performing the calculation? All right, back propagation. Thank you, Omkar. Correct. In back propagation, so the journey starts backward, right? Journey start backward. And when we saying, when we trying to say that in back propagation, we are starting the journey backward, like in input layer, we are passing the input x1, x2, x3, and you know all the step 1 and step 2 process which happens, right? Step 1 and step 2 process which happen, and out of that, we will be able to receive our prediction. And once we receive the prediction, we'll try to calculate the loss, and loss is not equal to 0, then that's how we need to understand that whatever model parameters I've chosen are not optimal. I need to go back. When I'm saying, guys, go back, can anyone tell me exactly what happens in going back? What do you mean by going back out here? Can anyone tell me going back means what does it mean? Right? So can anyone quickly tell me going back means what exactly it is trying to do? Checking error, Rish Kambli, yes. Checking error, gradient calculation, awesome, awesome. Vinod Babu sir, awesome. Gradient calculation, that's what I was looking for. So it is trying to do gradient calculation, adjusting the weights and biases on the loss, right? Correct, correct, Omkar. So your understanding is correct. So it is trying to do a adjustment, correct? It is trying to do the adjustment to the weights and biases. Okay, let's try to understand. It is trying to do adjustment to the weights and biases means what exactly we mean. Okay, we'll try to understand what the chain rule talks about today. Okay, just give me a moment, and then we'll try to talk about the chain rule. Okay, and when I am trying to talk about the back propagation, guys, back propagation means when I am going back towards the different layers, right? What exactly happens? Try to understand here. So in couple of minutes, I'll try to share the chain rule and how the actual calculation happening. That's what we'll try to focus. And then we'll go to the limitations, like what are the limitation which artificial neural network will be facing out here. All right. So let me go back. Just give me 1 minute and I will go back to this one. All right. So when see guys, when we're talking about, okay, when we are talking about these kind of equations out here, right? So when we're talking about, let me clear this one and let me show it to you in proper way. So when I'm saying that there is a backward propagation happening, means what happening? Let's imagine this is hidden layer 1, this is hidden layer 2, this is our input layer, okay, and this is our output layer OL. This we already know, and end of this output layer we are getting our prediction. And once we see the prediction, let's imagine take the same use case which we talked about, the BMI, body mass index, and let's imagine it predicted 25, right? The same example, and the actual BMI, let's imagine they are trying to predict the BMI of Vikas, and my actual BMI is, let's say, 30. So I am trying to calculate the loss. Actual, this is my prediction and this is my YI, right? So y hat minus yi, which I'm trying to do. So I'm getting a loss which is not equal to 0, right? So these are not 0. And that's what my optimizer has to do now, right? So my optimizer has to come into picture and the back propagation has to start. But when I'm trying to talk about the back propagation, what is happening? Let's try to understand that my entire objective of the back propagation is to make sure that, and this is not happening in one iteration, okay? Try to understand, guys. When I'm trying to talk about the neural network, so this is the flow, it is going forward, okay? It is trying to complete the one iteration, once half cycle of the iteration by doing a forward propagation, and end of the objective of the forward propagation is to create a prediction. And once we create the prediction, we are trying to calculate the loss, and then the second half of the journey starts for the neural network, right? And second half is like I'm trying to show you, it literally visiting all the layers one by one, all the layers. It is start visiting the loss function, then it will try to visit the of our prediction output layer, then it will try to understand. If you are able to see what are the weights are nothing but this connection, right, through which all the neurons are connected to next layer and to each other, right? So these are weights. So I can say weight 1 here, weight 2 here, weight 3 here, weight 4 here, right? And so on, weight 5, weight 6, and weight 7. So these all of weights plus the bias, correct? So these are called as my model parameters. So what initially I have to do is, when I'm trying to visit layer by layer, right? So I am trying to check what went wrong, because of which my loss is not exactly equal to 0. I am getting this kind of a difference. And then I need to start analyzing all the weights, right? So weight updation process means it's not a single weight which is getting updated, right? Okay. Try to understand out here what is happening layer by layer. They are going into the output. They are trying to find out what is the activation function as used, whether it is trying to perform correctly. And let me change the color here. Okay. Then it will try to visit W5 because it is the nearest weight. So it will try to understand what is the W5, W5, this weight 5 is playing a role with the output Y hat. Then it will try to visit this W6, then it will try to visit W7. Then they will move forward to this W2, 3, right, W1. And this is how one by one they are trying to create a chain. If you try to see the blue lines here, I am going one by one direction. It is like traveling the path, right? Traveling the path. So if I start traveling from this momentum, right, this position, and I want to reach back till the time I visit my input layer, right? At that time, I will go through the different layer, right? I will go through the different layer. So when I'm trying to talk about the W1 out here, right? When I'm trying to talk about the W1, I cannot directly see. If you try to see here, I have to go by path, taking the path, right? One path to reach to W1 could be I am starting from the output, then I am trying to visit W5, then I am trying to visit the W1. This is one path. Okay, I am sure this is more missed. So I will rub this thing and I'll try to explain you once again. Okay, so let's try to understand. If I am trying to go back, right, from the prediction, let's imagine I am trying to write here the loss, and the loss is not equal to 0. Now my back propagation journey starts, and one half is the forward propagation, the half cycle. Okay, half cycle is the forward propagation, and second half cycle is the back propagation. Back propagation means I am trying to visit all my neurons, all my layers one by one till the time I reaches back to my input layer, right here. So within that input layer also, let me write the things in the different color. So this is my weight 1, this is my weight 2, this is my weight 3, because this is what they are connected to each other. These are my hidden layers in between, right? Here for the simplicity we have taken only one hidden layer, and this is my output layer, right? Now let's imagine if you are starting the journey from here, loss, right? So from loss you have different ways to reach back. Let's imagine I want to reach back to W4, and prior to that, let's imagine there will be one more weightages out here, right? So when we trying to connect here, there will be weight 4 here. So I'm writing weight 4 here, W4, right? I'm trying to make it bold. So you guys will be able to see. Now let's imagine you want to go back, update all the things, and you want to go layer by layer, right? So layer by layer. So let me use the different color now. The one possible path which you want to take could be that you start from the loss, then you go visit this W4. Prior to that, there will be Y hat. Then you visit W4, then you will be possible that you can go to W1. This is one path. Or second path could be, guys, this way I am trying to draw in the green color. I start with the loss function, then I try to go back to Y hat, then I try to update W4, then I try to go back to W2, and from W2 I can connect to W1. So this is one more path, right? So this kind of a path means we're trying to create some kind of a chain, right? So it is very simple. What I'm trying to explain here is, if I want to update the weight 1, if I want to update the weight 1, I cannot directly jump from this point to this point to update the weight 1. See, if I try to write my equation, right? What is my equation to update the weight? New weight will be equal to old weight minus some kind of a eta parameter, which is a learning parameter, multiplied by my derivative of loss, right? Derivative of loss with respect to weight now, right? So this is what the simple equation will look like, but this is not that simple. When I am trying to calculate this derivative in terms actually contains the multiple derivatives. Why I'm saying multiple derivative? Because when I'm trying to calculate W1, right? When I want to update the weights of W1, this W1 depends on what? W4. This W4 depends on what? Y hat. This Y hat depends on the loss function. So this is kind of a chain which we need to follow. The path which we need to follow, or you can take a complex path also, like starting from loss, Y hat, then going to W2, then maybe you are going to W1. So this is how this equation will get spread, right? So this is what I'm trying to say, and this is what the short idea or the brief idea of the chain rule, because we are trying to create a chain here. So if in order to update the weight which is sitting at this layer, right, at the layer 1, and if I am at the layer 3, then I cannot directly jump from layer 1 to layer 3 to layer 1. In order to update the weights, I need to follow the path, and in between path, whatever weights will be there, right? So weight 1 will be there, this forecasting of the Y hat will be there. I need to update all the model parameters, then only I can reach to W1 and update the parameter. So the following this kind of a chain is called a chain rule, guys. All right. In derivative terms, if you understand, when I'm trying to say a chain rule, du by dx, right? Du by dx, or let's say du by dc. I can write this du by dc by this way, right? Du divided by dy, again multiply by dy divided by dc, right? So if I try to cross check this, if I try multiply and divide by the same term, it will still remain same, but I'm trying to create a chain here. The similar way, if I'm trying to update the weight 1 derivative, right? So this is the chain rule which we already know in the derivatives, that I apply and multiply by divide and multiply by the same term, the still the derivative will remain same, but it will start to create a chain, right? So kind of a u by v rule, right? So you know, guys, u by v rule, u into derivative of v divided by derivative of x into, now the v will stay, I exactly don't remember, but this is how the equation look like, right? So don't quote me on exact thing, but the v will remain constant and divided by derivative of du by dx, and everything divided by something like v square or something like that, right? This is what the chain rule in the derivative talks about. The same chain rule is applied out here in order to perform the calculation. All right. So I think you guys are able to now understand what is the chain rule. Let's go back to this topic. And this is where I will try to explain you how the chain rule will work, okay? How the updation process will work. So let's take the simple example, and then we'll try to create this one, right? So this is what the equation I am trying to talk about. Let me explain you what this talks about. Here I have taken hidden layer 1. Here I am taken hidden layer 2. Here I have taken output layer. Okay, this is my input layer here. Okay, so this is my input layer. Now these are W11 at layer 1. This is W12. Let's imagine this is W13, right? W13. So these are my 4 input layers. Then in the next hidden layer, these are getting connected, right? So this will give you output 1, O11 here. This is O12. And this will be O13, correct? So this is what happens. There will be 2-step process happening, and then there will be one more weightages here which will be connected, right? We are connecting to this O11 again will go inside this, and it will try to produce O21, and then same thing out here, this will produce O22, and this both the things will go inside this output layer, this activation function, and which will in terms create our y hat, right? the prediction, and then once we get the prediction, we'll try to calculate the loss. Now loss will be in this way, right? Actual minus predicted, and whatever the loss will get, if it is not equal to 0, then my back propagation start. And this is what the gradient descent is all about, right? This is my 0 point, and this is where we started initially at the AK point at random. And depending on the slope, you guys know, if my slope is negative or my slope is positive, I am going to perform the equation, right? If the slope is negative, then I'm going to increase my weights, right? Plus, if my slope is positive, then obviously I'm going to decrease the weights, right? This is what the formula look like, right? For the weight updation. Correct. This is what we have seen. Now try to look at the complexity. So first we have a 4 less 4. We have 4 neurons, then multiply by the 3, then multiply by 2. Okay, then we have a last one. Okay, this is what the neural network architecture look like, right? 2 hidden layers, then output layer. Now we'll try to understand how the weight updation process will happen and what is this chain rule talks about, right? So let's imagine, let me write it here and let me explain you like how the updation process will start, guys. Meanwhile, guys, if you have any questions or anything, you can ask me simultaneously and I'll try to answer you as well, right? So let's try to understand what is happening out here. Just give me one moment and then we can start this one. Okay. And I will try, let's take the example that if you want to predict the BMI, right? Or not BMI, let's imagine you want to predict that you want to predict that whether the person is diabetic or non-diabetic. Let's take this example, okay? Now we are trying to find out whether the person is a diabetic person or non-diabetic person, okay? So this is what the use case we are trying to solve. Let's imagine this way, okay? So your output should be 0 or 1. So if it is 0 means he is non-diabetic. If it is 1 means he is diabetic, okay? So this is what, let's imagine you are trying to solve. In order to perform the classify the person or identify the person, whether person is a diabetic person or non-diabetic person, right? So what all input could be, you need to pass, very simple, you need to pass could be a BMI, your BMI number, then your insulin level, okay? Then I'm taking very general example, guys. Then your gender, okay, insulin level, your gender, your BMI, okay. So, or let's imagine you can also take the number of pregnancies, right? So number of pregnancies you went through. If it's you are female, then gender female, and if you are female, then you're trying to go through the childbirth and all. This also will be taken into consideration, right? Age will be there, but as of now, I'm trying to keep a simple thing, right? So I'm trying to take only 4 input parameters as of now, right? So when I'm trying to pass this information, my end of the output should be either it should be 1 or 0, right? 1 or 0. If it is 1 means you are diabetic, it is 0 means you are non-diabetic, right? And let's try to do a dry run, right? Kind of a dry run. And by doing this dry run, how the information will flow, and we'll try to understand how the calculation will happen and how the chain rule will come into picture, right? How the back propagation actually happens. Let's try to understand here. So I'm passing this information, guys. Then once this information passes, this will be called as x1, this will be called as x2, this will be called as x3, and this will be called as x4. And accordingly, there will be different weightages available, right? This will be 1 1, weight 1 1, weight 1 2, there will be what 1 3, and let's imagine this is weight 1 4. Okay, these are the 4 weightages which are available because the thin connection which we are seeing here. So these are weights, right? 1 1. Now what is happened, we know the 2-step process which exactly happens here. So first thing, let me draw it with the different color now. The step 1 will be I'm take the BMI values row by row, right? So there will be this kind of a table architecture will be there, and I'm passing the structure data. Now let's imagine what will happen. Let's imagine I have 1,000 rows out here, right? 1,000 rows, and these 1,000 rows contain all these 4 information. So one by one row will go inside here, depending on the batch size you are trying to showcase, right? One row, let's imagine one row goes out here. So one parameter will be chosen. Then I try to perform the multiplication here, right? Applying the weightages to all the parameters. And once this happens, there will be summation happening into x into w, right? This is what happens, and this will go inside the activation function. So these are the steps which are happening here, and they will be able to generate this output, right? So whatever O11 is generating now with the BMI calculation, right? So same thing will happen here, right? With insulin also. So everything will get connected, all this information, then summation will happen, go inside this cell. Same information will also go inside the O12, and same information will go here also. So don't try to get confused that only BMI will get multiplied by this weight and go inside the further layer. No. So all the information are, that's why you can see that these lines are there, right? All the multiple connection you can see. So this x3, x2, x1, x0, everything going inside the first layer, first hidden neuron also, same information going here also, same information going here also, right? And that's why they are trying to generate output 1 1, output 1 2, output 1 3, and then there will be plus more weightages will be there, right? Up to here we have a 4 bits, then there will be W2 1 1, so W2 1, W2 2, because 2 1 2 2, and this will be W 2 3, right? This kind of weights will be there. Again there will be multiplication happening, and then again the summation will happen, and they will go inside, and they will be able to produce O1 O2, right? And this O1 and O2 will get again multiplied by one kind of a weightages, right? The W3 level, level 3 weights with 3 1 1 and W3 2, right? Now I hope I'm not confusing, guys. So you're able to understand, right, what is multiplication happening and how the weights are getting passed on here, how the multiplication happening, right? So again there is a multiplication happening, whatever the output generated, again at the end when we're trying to generate this kind of output, they were also getting multiplied by the weights, and the final activation function will be sitting in the output layer, which will be able to process and will be able to give you 0 or 1, right? 0 or 1. This is the y hat you will be getting here, right? Whether you are diabetic or non-diabetic, and they will try to compare actually with, right, which the reality figure, and you know, right, the subtraction happens, and they will try to calculate the loss, right? So this is what the forward propagation now happening. Correct? So everyone on the same page now, you are able to understand what kind of a complex. Now see guys, here we are creating only 4-layer architecture, right? Very simple, 4-layer. In reality, when people are talking about 150 layers, 200 layers, right? So try to understand what kind of a complexity we are there and what kind of a computation will be happening. Now this is just the forward computation. Now the real computation going to start, right? So guys, can you just quickly give me a confirmation that you are able to understand until now how our calculation has happened? So I can rub these things, and now I can start showing you the calculation for the backward propagation, okay? Or any doubts if you have, please let me know. So this is what is happening now, and we're able to generate the output out here, right? So let me rub this thing, and in the slides you are just for the simplicity, guys. Yeah guys, quickly give me confirmation, any doubts, any questions, or everyone comfortable now, understood what kind of a calculations are happening? We can go ahead now. Okay, thank you Vinod Babu sir, and a few couple of more people, guys, if you can give me confirmation, so we can go ahead now and we start calculating the derivatives. Now I will show you how the chain rule will work. Okay Onkar, thank you. All right guys, now let's try to understand. Now we are reached here, we generated our y hat, and then we calculate our loss also. So loss function I have already written here, actual minus predicted, and the loss function, let's imagine I am a non-diabetic, but I received 1 here, right? So I am non-diabetic, I have received 1, but actually I am non-diabetic. 1 minus 0, what will be my loss? 1. So now this 1 is not equal to 0. Now the actual calculation will start, right? So I need to make sure that, yeah, thank you Pratibha ma'am, thank you, thanks for the confirmation. Now my actual calculation will start, right? Now try to understand, guys. Now try to understand everything I have written here. Try to follow along with me, right? So this is W11. Okay. So for the simplicity, I'm just writing W11 here, W12 here, W13 here, and W14 here. These are my weights, right? And I'm not going to write the weights here. We'll try to consider these weights as these outputs only. Okay. O13, O11, OT, and then O21 and O22. Okay, O22. So this, you can assume this O22 also weights as a kind of a weights at layer 1. So this is layer 1, this is layer 2, this is layer 3, and this is my layer 4, right? So this is how we are trying to perform these things. Try to understand this way. Okay. So now actually I'm supposed to receive 0 and receive 1, right? So my loss is, now I'll be obviously I'm calculating loss. Loss is 1 now. Now I want to make sure that this 1 is, so this 1 has to convert it to near to 0, right? I should not be predicting as myself as a diabetic, since I'm non-diabetic. Now whenever I started at this point, that means whatever the, let me show you here. So there is a loss out here. So I will try to calculate this third dimension, where we'll try to calculate this as weights and this as a bias, right? So this weights and bias value, which refers out here, right, to this weights and biases value, and we have to reach to this 0 point, right? So whatever weights and biases value I have received here is not correct, right? So my journey starts now. In order to start my journey, now try to understand, I am starting from here, right? So let me change the color so it will become very visible for you. Now I want to start here, right? Y hat, from loss my journey starts, then I have to update my y. Then guys, what is the first step I can go is my output, right? My output y hat. So from output I have a 2 paths. Either I can go to O22, or I can go to O21, right? So these are the two paths. And from O21, let's imagine I want to update till here, right? OW1. So this is my main intention, that I want to update this weight now. Now why I'm talking about the chain rule, how the things will happen. Now let me write it the formula, right, for the updation of the weight for the derivative, right? So I already formula is written. I'll try to write it in better way. This is the formula W new, right? If you want to calculate W new, W old minus eta into dl by dw. This is my formula, right? So let's imagine here you want to update this weight, right? You want to update the O21. So for updating O21, what this O21 depends on? O21 depends on y, right? My y hat. So in order to write derivative of loss, right? Derivative of loss. This is where I start, right? Derivative of loss with respect to O, okay, O21, this one, okay, with respect to, this is my weight, right? So, or I can write as W, just to remove the confusion, I can write O21 as W21. So in order to create this equation, what I can write? So this O21 now depends on what? O21 depends on my y hat, right? Y hat. So I can rewrite this equation. Let me rub these things here. I can rewrite my equation here. How can I rewrite my equation here? So this way, this DL divided by, now this W21, right? So let me write it in bold way, so you guys will be able to understand this O21, this thing I am talking about, right? O21, if I want to update, now O21 depends on one y hat. So DL by dy hat, right? Dy hat multiply by dy hat divided by D21, do D21. Okay, this is what the derivative will calculate now, correct? So this is very simple. DL by dw1, it is this depends on the y hat. Then I am trying to multiply and divide by y hat, and then I am trying to write. This is what the equation will happen, and this derivative will be taken. This derivative will be inputted here, and then they will try to update the new weights, right? So that is very simple. Now you understood, right? So this is simple one rule. Now let's imagine. Let me rub this thing now for the W21, right? So let me rub this thing for the W21. Let's imagine now you want to go further, right? This is very simple. But even though this is simple, we are trying to take the partial derivatives. Now let's imagine you want to update this weight right now, O21. Now if you want to update, now let me ask you from you guys, okay? So I want to write the equation DL by D O11, right? This O11. Now how should I write? Can you tell me now? How should I write? By following the chain rule. Can anyone tell me how the weight updation will start here? What kind of a derivative will come into picture? Now you have to decide. Okay, I will give you hint. Now O21 is depend on what? O21 is depend O11, sorry, O11 depend on O21, and now O21 is depend on y hat, right? And then y hat will come to loss. So we are trying to write the equation DL by O11. This one, DL by O11, right? This is O11. So if I want to write or update this equation O11, what should I write here? What kind of a terms will be coming into picture? Can anyone tell me quickly now, guys? I know it is going bit complex, but try to understand. This is what the mathematical background. This is the maths which is happening in the background, guys. This is what is happening. It is very simple. This is called a chain rule. So that's why I'm trying to make you simple and try to make you understand. Okay. So if you are trying to update this weight is directly depend on y. So I can write directly here, right? So what I wrote is y dl loss function, right? Loss function divided by y hat multiply by again y hat divided by, then I wrote this one O21. So right, so this O21 which actually gives me the O21. Now the same way, if I go to O11, now tell me guys quickly, so how should I write this equation now in the terms of the chain rule? So let's see who will be able to tell me the equation. Okay, so now simply you have to add the terms, guys. Keep on adding the terms. Now I will try to write the same equation here. Okay, let me rub these things and let me write the same equation here. So there will be no further mess here. So you guys can easily understand. Okay. Let's see. Okay, let's see. We have written DL derivative of L divided by derivative of O1 into multiply by. Yeah, you are close, SR map, sir. You are close, sir, map. Yeah, but not exactly. Let me show you again. So let's try to understand from this point of view. Okay. So let's try to understand, and let me write it in simple way, and then we can start understanding it. So see here, we are starting from loss. We are going to y hat. Okay. From y hat, we are going to this one. Okay. So this y hat, and then from y hat, we are going to O21. and from O21 I need to reach to O11. So let me write the equation, right? First I will try to write the equation of O21. Okay, then we'll try to generalize for O11. Okay, we only need to reach to this previous layer. So now I am trying to update. This is my equation: old weight, new weight equal to old weight minus eta into derivative of dl by dw. Now these w's are different, right? At any position, whenever layer by layer you are going, the w's will be different, right? This w now we are trying to calculate. Let's imagine they are calculating for 2 1. So I will write 2 1. This I am talking about, this layer. So in order to reach to 2 1, how I am going, how I am trialing, from I am starting from the loss, then I am trying to visit my prediction, right? Dy y hat, then multiply by y hat, then divide by, then I will try to write this one, right? W21. This is how the chain will be formed, correct? So in order to add now, let's imagine in the same equation now I am going to add, instead of now W21, okay? Instead of W21, if I want to go to O11, right? So here I am writing 1 1, layer 1, right? This I am talking about, this form, right? So in order to reach this one, now I will be starting again same thing, y hat, then from y hat I will be going to this one, O21 plus multiply by D21 divided by this 21, this will happen here, W2, then I will try to reach here, right? O11, W11, so W11. So this is how the equation will look like. Okay, understood guys? Or should I write it again? Let me write it again. Let me rub everything and let me write it again. If you want to update this weight, right? So I am starting here, derivative of loss with respect to weight. Now what is my weight here? Weight will be at W11 layer, right? So this 1 layer, 1 So this W11 layer will depend on what? So DL, let's start from the beginning, from y hat, right? So I am going to write here y hat, again multiply by y hat. Okay, so divide by what is the next step? If I try to cover, I'm starting here, this is my L, right? So this is my y hat. From here, let's imagine I can take this path or I can go this path also. Let's imagine I have taken this path, O21. So write O21 here, O21, correct? Multiply by, then go to this one. So again since I am dividing, I need to multiply also. So I'm multiplying by O21. So then I am reaching to O11. So O11 or W11, same thing. So this is how it is trying to form a chain, correct? So this single equation O11 will be depend on this many derivatives. So in simple thing, guys, in simple thing, if I try to understand the chain rule says that if you want to update the weight at any point of time, you need to follow the chain, and whatever the terms are coming, you need to consider them while taking the derivative. So in order to reach to this point, I have considered starting from the loss. So I consider y hat, from y hat I reach to O21, O21 to O11. This is what I have taken into the equation, guys. Awesome. Vinod Babu sir, you are correct. So you are taken correct weight, O11. Correct. You already given us correct equation for the O1. Correct. So same way, guys, now we need to update this one. So I will keep on adding here. Need to add here. So now this multiply by W11, again multiply by W1, then this. Okay. So this I am trying to write about this 1 layer, right? So this 1 layer, again dl by dy hat, multiply by y hat by O21, O21 again multiply by O21 divided by O11, W11, then not W11, O11, and then O11 to this one. Okay, so this call this as 01 maybe. So this way. Okay, this, or you can call this W, or this call as O, right? So this W11 multiply by W1 and then W by 01 or whatever, or let's rub it and make it very simple here. So I'll give the proper names. So this call this as W11, then I'll call this as W21, and then this I will call as this 21, then this will be 31. Okay, this will be 31, and this will be y hat, right? Yeah, correct, sir. Siddharth Ghosh, sir, correct. So this is what the chain rule means, partial differentiation we are taking, right? So if I want to update this weight now, let's write the equation. So this equation is already there, right? You know how the new weights happens, right? So you start here based on the slopes, whether it is positive, negative, you go down either or you come up, increase the value, right? And then we try to find out the loss. So new weight equal to old weight minus learning rate. This learning rate is nothing but, guys, it is trying to decide, right? You want to increase and decrease the weights, the magnitude or the scale by which you are trying to increase or decrease the weight, like whether you want to go one scale down you want to go 2 scale down, that is decided by this learning rate. Okay, LR, learning rate. Learning rate is denoted by eta here. So eta decide the speed at which you want to jump, speed of jump. So how you want to jump for your weights, right? So this is what the jumping speed is decided by the eta. That's why we are taking learning rates, right? That's why we cannot take high learning rate. And what I told you, people usually take the learning rate with this way, right? 0.10 or up to 0.10. So this is the range they try to take, not too much, not too high. If you are trying to take too much, very high learning rate, simple, what will happen? You need to go to this 0 level. It will try to jump here, 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 here. This is the jump it will be happening. It will never reach here. Or if you want to take the very slow rate, now what will happen? If you start at this position, now this will happen. Then you will go here, 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 then you will go. So in order to reach to 0 point, too many iterations, right? Too many iterations you will take to in order to reach to 0 point. So that means maybe 1000 iteration. So it is very cost computation. Now let's go back. Let's go back and rewrite one equation. I hope it is very exciting, guys. I hope I am not making you bored, right? This mathematics is very important, guys, in order to understand this one. Okay, what is happening in the back box? Okay, so that's why people call this as back box. This is not back box, guys. This is not magic. This is mathematics. Okay, this is derivative, this is stats, which we learn, which we try to avoid during our 11th and 12th, right? So this is 3. Okay, so this is 3 1. So let me rewrite the equation using the chain rule. Now if I want to update this weight, right, W11, so this W11 now will be depend on starting from the loss to y hat to this one, from this to this, and from this to this. So this is one path, or second path you can take. Okay, this is very simplicity I'm talking about. So you can take this path also. From W3 you can diverge to this one also. Then you can go here and then you can update this path also. This could be possible. Whatever path you are taking, that many derivative terms will get added. Or you can start by this path, come here, then you can go and you can go part this path also. It could be possible. It will try to take the several combination, guys, and then they will try to optimize. That is why that many billion parameters. Now you are trying to understand, right? So what kind of a calculation we are trying to talk here? So let's write this one. Now derivative of loss divided by y hat multiply by y hat. Okay, divide by 3 1. Okay, again multiply by d31 multiply by d. Okay, 2 1 W21. Okay, W, this is W, again multiply by W21 divided by then W11. So this is how the equation will look like. If you want to write DL by loss, take the derivative of loss with respect to this weight W11. Okay, this is what the equation will look like, right? 3 1 multiply by 3 1, then 2 1 multiply by 2 1, then 1 1. All right, guys. So if I'm trying to take this path or other path, that many derivatives simply you have to add here. So if you are trying to take this level here, so what is this level? This will be 2 1 1, right? So this is W22. So you have to add here W22 and then multiply by whatever equation you are trying to take here, right? So let's imagine you are trying to take this W22. So divide by then W21. This is one more derivative we'll be adding here, correct? Hope you guys are able to understand what is this chain rule and how it is trying to update. And this way, guys, this will be the multiple paths you can take here. You can start from this path also. You can go here, or you can go by this path, this path, this path, this path also. And this how the every layer, the weight. This is called as back propagation now, correct? With the chain rule, guys. Okay. For your simplicity in explanation, I already written here this equation. So this is single equation. Okay. So I think I was able to make you understand the simplicity we have written here. All the equation, if it is this one, if you are trying to calculate the W311, this weight, so this is very simple. This is depend on this one and this is depend on, right? So this is depend on this one, derivative of loss divided by O311 multiply by O311 divided by O11. Simple, right? So it is very near. So when you try to go this far, then multiply again but different weight. So W11 at layer 3 divided by W11 at layer 2. Okay, this how. So if you want to go here at layer 1, this is layer they are talking about here, 1 2. So this is the 3 layer, right? Correct. So if you want to go further again, so try to multiply by W11 at layer 2 divided by this one, this term, right? So W11 at layer 1. So this is how it will become 1 1, correct? and this is how it will try to update the new weights. All right, guys, this is called a chain rule. This is very simple. In fact, you just need to understand that whatever path you are taking, try to adjust all the parameters, multiply and divide by same terms. You can see 0311 here, divided, then multiply by 031, then take the next one, then keep on adding. Okay, this is how the chain rule will be formed. All right, guys, I know it was very technical, very mathematical. So just to have your views, can you just quickly tell me, comfortable, you are able to understand? That is not difficult. You guys are already very deep into the topics, I know. So it will be not a piece of cake for you guys, hope. So just quickly give me the confirmation. And this is the next slide which I covered. You can go back and check when we try to calculate the 011, what kind of a equation will be written here. Okay, I have already covered here. In this equation, 011 will try to calculate these many terms. Okay, so this, for simplicity, I already included. You can go back, refer any point of time. All right, guys, quickly give me confirmation. So let's try to understand your understanding whether we are all on same page. So we need to cover today implementation as well, right? Quickly give me some confirmation, any doubts, any question as of now, and then we can go ahead. Then we'll try to understand vanishing and exploding problem. All right, so everyone is bit quiet now. What happened, guys? Clear? Omkar is saying yeah. Yeah, Ghosh sir, I guess it will be very easy for you to understand, right? Clear? Yeah, couple of more people, guys, if you can give me confirmation. Clear? Any doubts? Yeah, okay, we are on track. Okay. Yeah, Krishna Joshi, ma'am, sir, if you have any question, please ping me here. Clear? Okay. All right, all right. Clear, sir. Thank you. Okay, Dr. B. Srinivasan, thank you. So, guys, let's try now together. Just pull all the pieces together. Now try to understand what is happening. Okay. Now just pull the pieces together and try to understand now what will happen. Let's imagine this is the input you are giving, right? Picture. Now once you give the picture, this will be become your training set, and it will go through the layer by layer, right? So layer by layer, it will the step 1, step 2 process. Then this connection you are seeing, it will try to update the weights, and in the end you will try to receive this kind of output, right? Y hat. So y hat is cat, but actually it is dog, right? So it is saying it is cat, but it is dog, right? It's mammalian dog. So that's what the differences we have. Then it will try to calculate the error. Then it will try to go back layer by layer, layer by layer, layer by layer, try to update the weights until the time it reaches to it, right? And you know already that we'll try to talk tomorrow about the convolution neural network. I'll just give a brief view and try to implement one convolution neural network. I'll also talk about Keras tuner, guys, tomorrow. Okay, Keras hyperparameter tuner. So how we can tune the hyperparameters of the deep neural networks, okay, by using the Keras tuner, Keras hyperparameter tuner. This is what I will try to showcase you from the coding point of view also tomorrow. How can we use the Keras tuner to fine tune our model parameters, okay, hyperparameters, sorry. So this is what the in general, just to connect the dots, I've shown you that how the process will happen, and this is where our neural network will fit in. Actually, here there will be two neural networks. One will be convolution block plus ANN will be there, since it's a picture or image, right? Even we can give a picture to our ANN alone also. I'll show you that example also possible tomorrow. So where they will try to create one flatten layer, and then we'll try to plus this. This flatten layer will contain the matrices which contains this information about the picture. Okay, this how the things will happen. So let's move ahead, guys, without wasting much of the time here. So let's this for the understanding we have created. Now try to understand what do we mean by vanishing gradient problem. Okay, let's imagine what is vanishing gradient problem and what is going to happen here. So in simple terms, anyone would like to guess what could be the vanishing gradient problem, guys, when we're trying to talk about the vanishing gradient problem? Okay, so anyone, any guesses what could be the vanishing gradient problem actually? So what is the gist, one liner? Anyone would like to contribute? Let's see. What is your understanding? What do you mean by vanishing gradient problem? What it could be? One liner will be more than sufficient. Okay, gradient almost negligible. Awesome, awesome, guys. Awesome. You already know, right? You already know. Very technically superb answer, Vinod sir. Thank you. Vinod Babu sir, thank you. Okay, guys, let me tell you. Okay, let me tell you. Okay, forgot previous information. Could be possible. Yes, Omkar. So guys, let's try to understand. In simple words, if I'm trying to say, right, we are moving here, input layer, hidden layer to output layer, and we are going back, right, layer by layer. Now, this was very simple architecture we're talking about. Let's imagine we have this many layers here. This is one more layer. This is one more layer. Okay. This is one more layer. Now, what is our weight updation formula? New weight equal to old weight minus eta learning rate into derivative of loss with respect to derivative of weight now. So let's imagine now, and why, what is vanishing gradient problem? In one liner, if you want to understand vanishing gradient problem can be understood in two ways. Okay, two ways. One is, guys, the gradient. Okay, when you are having a huge neural network, at that time possible that your derivative gradient was, why we are calling gradient, you already know it. We are taking partial derivative gradient. That means we are taking derivative of loss with respect to weight. We are taking derivative of loss with respect to bias, right? Two derivatives we are taking partial. Now, when we're trying to focus mostly on the weights, right? At that time, let's imagine this derivative, when we try to take the multiple times, right? We are taking multiple times. We are taking here derivative. Let me give you very single example what I'm trying to talk here. When we try to take the multiple derivative, what will happen? This derivative tend to become zero. This derivative tend to become zero when we try to take the multiple time derivative. Let me give you example. Let me ask you, okay? So what is the derivative, guys? What is the derivative of x square? Can anyone tell me? What is the derivative of x square? Let's take the simple mathematical calculation. You only come to know. So first time I am taking derivative now. Derivative number one. So let's imagine d by df, d by dx, dy by dx at 1, x square. So what will be the answer, guys? Can anyone tell me? Okay, 2x. Awesome. Correct. So 2x. Now let's take the again derivative level 2, d by dx 2. So what will be the derivative now after of 2x, guys? 2, correct. So now derivative 2. Now take the derivative of level 3. So take the derivative of 2. What will be the derivative, guys? 0. Now you come to know what is happening. When I am taking multiple times derivative, my derivative tend to become 0, correct? My derivative will become 0. So this was simple equation here. But when I'm trying to move from layer 1 to layer 2, layer 3, layer 4, lower 4, back, till the time I try to reach input layer, guys, what will happen? You are taking multiple times derivative, right? You are taking derivative here, you are taking derivative here. All the layers you are visiting, you are taking derivative, correct? So what will happen? One point of time, your derivative become very close to 0. Your derivative will become very close to 0. Now I'm not saying it will directly become 0, but it will be very close to 0. Now let's try to put this into the equation, and then you will understand when the derivative becomes very close to 0, what will happen. Our learning process will stop, guys. Our learning process will exactly stop. Let's try to understand this one. Okay, and let me tell you, vanishing gradient problem means our weight updation process, whatever the weight updation process we are doing, our model stops learning because of these gradients are becoming close to 0, or there is a no significant change in the weights. Okay, if the weights are not different, weights are not getting changed, or weights are getting stagnant, means my machine learning model will, or whatever this artificial neural network is there, it will stop learning. So that's the reason it is called as vanishing gradient, means gradient becoming close to 0. Now let's put this example. Okay, let's imagine initially I took old weight as 4. Okay, old weight as 4. Now let me tell you one more thing before we deep dive into this. Okay, so this is problem which is happening because of the sigmoid function. Okay, sigmoid activation function is responsible for this. So whenever people try to talk about this vanishing gradient problem, so it is happening because of the sigmoid activation function. Because I will tell you, when we try to take the sigmoid activation function and we are trying to calculate the weights, so it will give you derivative between 0 to 0.25. And this is the range. You can go ahead and calculate the sigmoid derivative. You'll find out the answer. You can search also. So this vanishing gradient problem mainly occurs because of the using of the activation function, which is sigmoid of activation function. When you use the sigmoid activation function and when you try to calculate the derivative will fall between the range of 0 to 0.25. Okay, so let's imagine this way. Now I am calculating new weight. Okay, my old weight is, let's say, 4. My learning rate, okay, my learning rate is, let's say, 1. Now if this derivative, now what I'm saying, if I'm using gradient, when I'm trying to calculate gradient, I'm using sigmoid function, my value will lie between 0 to 0.25. Let's imagine it is trying to fall between higher range now, as of now, first time 0.25. This derivative's answer is 0.25. Okay, so let's calculate now. New weight equal to 4 minus 0.25. So this way, for simplicity, and don't quote me an example, so this will be between 3.75. So is there any major change between 4 and 3.75? Let's try to understand from our graph, right? This is our graph. So this is where I started, point AK, and this is where I need to go 0. Okay, make my loss 0. and these are my weights and biases, right? So this is my weight and this is my biases. So if you start here, let's imagine this is scale 4, and if you are going to only scale 3.75, so what is happening? Is your model learning? There is not much difference, right, in the weights. So your learning is not that great. Means from this moment, this point, okay, let me use the different color now. So where you started at AK, now you just moved here. That's it. So that's the reason this is called as vanishing gradient problem. Means when you passing from layer 1 to layer 2, there is becoming a stagnancy. Your gradient becomes so very slow, very low, that the whatever layers you have here, okay, whatever the layers you are talking over, this layer to this layer updation process is very slow, or it is negligible. It is negligible. Your weights are not getting updated. Weights are not getting. So this is the reason, right? This is the reason weights are not getting updated, because you can do anything, but your derivative initially will fall between this range only. So this is the first time. Let's imagine after 5th or 6th time, if you are taking the derivative, now what will happen? Let me rewrite this formula. Okay. So let's imagine this is 4. Okay. Take the learning rate same, and this imagine this becomes 0.1 or maybe 0.1. Okay. So this derivative becomes 0.1. What will be the equation? 3.9. So you are moving from 4 to 3.9 only. Okay, let's imagine this way. So what is this? I am not learning anything. I am not learning anything. This is called as vanishing gradient problem. Cool. And this is mostly happening because of the sigmoid function only, sigmoid activation, because sigmoid's derivative fall between 0 to 0.25. Cool. Now understood what is the problem, guys? So the vanishing gradient problem in one liner, if you want to say that the gradient after multiple times when you try to take the gradient tend to become close to 0, because of which the weight updation process will stop, or it will become very very negligible. Weight updation process will be stagnant at the some moment. But less, and when this happens, mostly when this happens when you have a multiple hidden layers, or your architecture is very high. Let's imagine you have a 10 layers. At that time this will happen. Yeah, correct. Because of the small changes and computing resources are utilized more, the performance decrease. Correct, sir. So what could be the solution? What could be the solution, right? So what could be the solution? This is called as vanishing. Means your new weight and old weight, there is a very negligible difference between the weights, right? So weight updation, it is almost same as the previous weight. So if your new weight and previous weights are same, means your model is not learning anything. Your artificial neuron is not learning anything. So how, if it's not learning anything, how will optimize our loss to 0? How will I optimize my loss to 0? That's the reason. So that's the reason that I need to avoid this vanishing. This is the one problem we'll face, right? When you have a multiple layers, when you will try to take multiple derivatives, and when you're trying to use the sigmoid function. So what could be the problem? What could be the problem? How can you solve this problem? Simply use the different activation function. Make sure that you are not trying to do in deep, right? You're not trying to create this kind of a deep neural network unnecessarily. So you will again ask a question, sir. There are ResNet and kind of architecture which have around 150 to 250 kind of a layers, right? So but if you try to go back to their architecture, they are not using sigmoid everywhere. They are using maybe 10H function. They are using something called as now ReLU function. So then they are trying to create this kind of a deep neural network which contains this many layers, 250, 150 layers. Okay, this kind of architecture they are trying to create out here. All right, guys. So I guess you are able to understand this is the problem you will face when we're trying to do a back propagation. So this is the first problem, vanishing gradient problem, where your gradient become very close to 0. Okay. So now next problem what we can face. Okay. So let's try to go back to the next problem and try to understand. The next problem will be exploding gradient. Now can anyone guess by looking the name, exploding gradient problem? What could be the issue here? So exploding gradient problem. Anyone would like to guess what is happening out here in exploding gradient? It is quite opposite to vanishing gradient, guys. It is quite opposite. Let me write the formula. My new weight, okay. Let me rub this thing. My weight new will depend on weight old minus learning rate into DL by DW, okay. So this problem will happen. Anyone, guys, quickly who would like to guess in exploding gradient what will happen? It is quite a opposite term to vanishing gradient, okay. Exactly opposite will happen. So if in one liner, if I want to explain this one, so in exploding gradient descent, my weights are getting very different, okay. So whatever the old weight is there, my old weight and the new weight, they are very, the difference between old weight and the new weight will be very high. very high, and because of this high rate difference, okay, because of this difference which is very high, my model will also not try to converge fast. My conversion point, okay, when I'm trying to converge, what do you mean by conversion? Conversion means going to 0 point. Now, so now I'll tell you what is happening. Let's imagine you started here, okay. So now the actual problem, this problem is not happening because of the sigmoid, guys. This problem is happening because of the differentiation. Whatever the derivative you are taking, this derivative is very large. Maybe this derivative values could be 100, 200 or something like that, or could be 50, okay. So this conversion point will not occur fast. This is our conversion point where the derivative will become close to 0, right? So this is what we want to achieve. Now, in order to achieve this, what is going to happen? Let me write it here. Okay, let me write the formula above. So okay, not derivative exactly. First, let's write the formula of the weight updation. New weight will be equal to old weight minus this learning rate into derivative of loss divided by weights. Okay, now what I told you that in exploding gradient problem, the weights are very different from each other. There is a huge difference. Okay, there is a huge difference between the weights. Now let's imagine this way. Okay, so initially let's take the same example. Initially I took the weight 4, then let's imagine I took the learning rate as 1. Now this derivative value is very high as compared to the previous value. Okay, so this derivative, let's imagine it's coming to 100. Derivative is 100. Now what will happen? 4 minus 100, so minus 96. Now let's imagine you started here, right? So this was the mark of 4. Now from mark directly you are going here above, right? So 96, or maybe you are going down, minus 96. Then from minus 96, let's imagine. So minus 96 is your old weight minus learning rate 1 into, again next time it is, let's imagine it is like 100 now. So what is going to happen? Minus 96 into minus 96 minus 100. Now 196. Now what is going to happen? Now you are jumping here. Now here. So that is the problem, guys. That is the problem, that your derivative is very high, very derivative value. This is not because of the sigmoid. Now let's try to understand. Sigmoid was trying to take your derivative between the scale of 0 to 0.25, because of which your derivative was trying to get close to 0, and there is a weight updation process was not happening clearly, right? Rare by rare, it was not trying to take it to the 0. Now here what is happening? Actually it is happening quite opposite. Whatever the derivative value we are having, the derivative is having very high values, and because of this there is a huge difference. Because of this there is a difference between the weights, right? Whatever the old new weight is there is a huge difference between the old weight, okay, because of this derivative. This is again happening because of derivative. All right, so this is the reason. Okay, this is, and then if we're taking very high derivative, means imagine you start here, so you'll go here, from here you'll go here, again here, again here, so you'll never reach to the 0 point. Again same thing, just like the learning rate. Okay, so that's the reason it is exploding. Exploding means it is trying to create very huge changes. Okay, that's the reason you'll not be able to reach to the 0 point. All right, so let's go down, guys, and I hope you are able to now understand. I have given you very good example also. You can see here, going back with respect to the time, the vanishing means your derivative become very small, and exploding means when we go back with respect to time, with respect to the layer, your derivative become very large, it start exploding, and that's the reason you will never converge to the 0 point. All right, guys, so any question, any doubts as of now on how to handle, right? How to handle this one? So truncated back propagation, gradient clipping, or weight initialization initially, or then you can go for the other neural networks also. So if you try to face this kind of things, right? Or one popular option could be regularization here. So that is what is called as dropout layer here, regularization technique now. Okay, so dropout is kind of a regularization technique. Can anyone tell me, guys, why will require a regulation technique in first place? Okay, so I'll require the regulation technique in first place, and to explain you how the regulation technique will happen, what is dropout layer here. Okay, so can anyone tell me what, and let's try to understand when guys, when to solve this, when to introduce this regulation. Anyone quickly? Why will require regulation techniques in first place, right, in the neural networks? Can anyone tell me? We already discussed this couple of examples. Just to make sure everyone is on the same page, let's try to understand what is the reason that we'll require these kind of things. Yeah, guys, and yeah, overfitting, and awesome. Data normalization, awesome, correct. Reduce overfitting, correct, reduce the overfitting. Or could be possible that you are near yeah, because of this vanishing problem also, guys. Vanishing, if you try to understand here, if you go back here, okay, Now people, what they said is, if you try to understand this one, they're saying that do the gradient clipping. If you are facing vanishing gradient problem, do the gradient clipping. Gradient clipping means they are trying to talk about, try to reduce the calculation. Try to reduce the number of derivatives you are taking. Number of derivatives you are taking, right? We have seen that if I try to take the multiple derivative, let's imagine you start with the x square, then you will reach very zero at the third level only. Third time if you try to take the derivative, you will reach zero, right? You will get a zero derivative. So they are saying do the gradient clipping. Gradient clipping means what? That means they are trying to say that try to reduce the calculation of the derivatives, right? So how to reduce the derivative calculation? By the dropout layer. Now we'll talk about the dropout layer. Okay, so you guys already gave me some answer, right? What is dropout layer? Dropout layer in one liner. Okay, dropout layer, guys, let me tell you, dropout layer is helping us to regularize the neural network. Okay, regularize the neural network. So what do you mean by regularize the neural network? Means it is trying to take care of the overfitting, it is trying to do the gradient clipping, it is trying to take care of the exploding and vanishing gradient problem. In simple terms, if you try to look at this graph, okay, so let's imagine this is your neural network. Now in this neural network, if I'm say dropout, means literally I'm trying to drop some of the neurons. I'm trying to drop the number of neurons at a time, number of neurons, okay, number of neurons at the time of the training, at the time of the training. This is the literal meaning of the dropout. So if you want to say dropout, what exactly? To create non-linearity in network. Awesome, correct, guys. So if you say that this is my input layer, okay, this is my input layer. In input layer, how many neurons I have? 3. Then this is my hidden layer 1. This is my hidden layer 2. This is my hidden layer 3. And this is my output layer. Okay. Now here also I have 3, 3, 3, and 3. Okay. Everywhere. So now what I'm trying to do? I'm trying to hide one neuron here. I'm trying to hide 2 neurons here. Then I'm trying to hide 1 neuron here. I'm trying to cross. You see the cross? Cross means I'm trying to hide the neurons. Okay, I'm trying to hide the neurons. And then I'm trying to train my model. Then train my entire neural network. Now, how many neurons I have hidden here? 1, 2, 3, 4, 5. That not I'm taking from the entire exactly the entire dropout. There is a percentage of the dropout which you need to decide. And the percentage lies between 0 to 1. And what do you mean by dropout? We're trying to hide some of the neurons while we try to train. Now, when you try to hide means obviously the derivatives, this weights, derivative with respect to weights, you are trying to reduce this calculation. So this way we can help in creating the avoiding the vanishing or exploding problems, right? So since you are actually trying to deactivate, right? You are actually trying to deactivate. So you can take care of the vanishing and exploding problem this way. Since you are trying to deactivate, are we deactivating them permanently? No. We are doing this iteration by iteration, or you can say epoch by epoch. Okay, epochs, it is called as epochs or iterations popularly. Iteration means if you are trying to train your model 10 times, right? So first time I'll try to hide these 2 neurons. Okay, so in iteration number 1, so second time in iteration number 2, then I'll try to calculate my y hat, then I'll try to update my weights. Okay, and second time what I'm going to do, in second time whatever neurons were hidden, I'll try to activate them, and I'll try to deactivate the other one, right? Other one. So in second one, then third one, again different combination. Now it depends on the what percentage you are taking from the dropout. Dropout percentage stand between 0 to 1. Okay, dropout percentage stand between 0 to 1. 0 to 1 means starting from 0% to 1% means 100%. So you can go by 20%, you can go by 50%. Don't try to go by 80, 90. Otherwise your entire neural network will go haywire, right? So when you have a huge neural network, at that time you can go for the higher values, right? So I guess, and these guys, let me tell you that when they try to propose this AlexNet, right? This is the first neural network they tried before the LeNet. What? LeNet. Okay, LeNet was the legend Jan LeCun. Okay, Jan LeCun. This was the name of the legend. He's the head of the Meta AI at AI, right? Head of the Meta AI, Jan LeCun. This was the guy who introduced the LeNet in 1998. Okay, so this was the first architecture proposed for the artificial neural network, LeNet. And this LeNet, then the Jeff Hilton guy, the Jeff Hilton, he was the head of the Google Brain, one of the legend. Okay, head of Google Brain or Google AI. Okay, who's responsible, who late just now a few months back because of the safety concern. Yeah, ma'am. Thank you, Rajeshri, ma'am. Thanks for asking. Okay, guys. So these guys, they first introduced this kind of a proper dropout layer. Okay, so let's try to understand this one when we're trying to talk about the dropout one. Okay. So let's come back to the slides. Okay, guys. So let's simply try to tell me that let me tell you that the history when we're trying to talk about the dropout layer. So it was the Jeff Hilton, right? This was one of the legend. He's the head of Google Brain. Now he left the Google Brain because of the safety and security concern, the concern over the ethics. And one Indian guy was there, Nitin Srivastava. These guys, they first brought the paper in 2014 called as dropout concept. Okay, then this entire regulation happened and they try to take the L1 L2 regulation, dropout regulation, and that's how the okay guys, thank you, thanks for the compliment, ma'am. Okay, so guys, this is the first time the Jeff Hilton, Nitin Srivastava, they introduced in the AlexNet, and then how the people started to take care of it, right? So literally, if you try to say here, the whatever the red color neurons are there, yeah, guys, you'll get the Wasim sir. Yes, you'll get the attendance. Okay, so in couple of minutes, you'll get the attendance by 4:35. Okay, so guys, here this dropout ratio P is called between the 0 to 1, and depending on that, you can create the dropout layers, right? And in the dropout layers, I told you layer by layer. Let's imagine here, if I try to take the 50% dropout, means what will happen out of this 4 neuron? If you see the 2 neurons are red color, so these are 50%. Okay, here if we have 6 neurons, out of that 3 neurons I will be making off, right? 50%, and similarly out of this 2. So this is the first iteration will happen, and then we'll try to calculate or update our weights and biases, correct? So this is in first iteration. Then in second iteration, opposite will happen. So I am trying to draw then with the black color. So whatever the initially hidden, they will become active. Now the other one will become deactivated, which I am trying to showcase in the black color. Okay, so this black color one will get deactivated and the red color will get activated, and then they will try to calculate. This way we are trying to avoid everything, correct? So this is what the entire what you can say dropout will work. And but in the end, if you try to see here, everything will get activated again. Everything will get activated, and then the final y hat will be created or delivered to us after several epochs. Okay, after several epochs, our loss will become close to zero, and our final prediction will come out. Now you can see the clean one. Okay, every neuron is active, and we are trying to receive the y hat. Okay, and then if you say that how to find out the optimal value of P or the dropout here, so by using the two algorithm, grid search and random search CV. So what this algorithm, I will tell you, this grid search and random search is nothing but they are just trying to take the value. Let's imagine you have to give a range of the P. Now this P will be called as dropout, so DP. So you can give the range between 0 to 1 for the dropout. Then you can give a range, let's say optimizer here. Okay, optimizer. So you can give two optimizer. You can say SGD, stochastic gradient descent, or you can say Adam. Okay, so this range of the values you have to give for the different parameters. Then you can say like a number of let's say neurons, or let's say activation function. You can give a couple of activation function, number of input layers or number of hidden layers. Okay, so regulation. So this kind of a range of values you have to mention, and that values will go inside this grid search function, and then they will try to run with the different combination. Yeah, both, Banushri ma'am, yes, both will work on CSV data. Any data you pass on, it will work. So now what they're doing initially, so they are trying to take the permutation and combination. They will try to take the permutation and combination. Okay, permutation and the combination of these values, right? What will happen? First time they will take P equal to, let's say, 0.1. Then they will try to take the optimizer equal to stochastic gradient descent. Okay, then they'll try to take the next one is number of hidden layers, let's say two hidden layers. So this combination they will create, and they will try to find out the weights and biases. Okay, and they will try to find out the accuracy score, accuracy 1. So next time they will try to change the values here. So this way, combination 1, permutation 1, permutation 2, permutation 3, and they will try to come out with accuracy 2, accuracy 3, accuracy 4. And out of this, all this one, whatever the highest accuracy is there, that highest accuracy parameters, okay, highest accuracy parameter, which will be given by best underscore parameter. Okay, best underscore params. Okay, this is one of the option here in the grid search and random search. And if you try to print best underscore params, it will give you for what values. Okay, what values of this dropout, what value of this optimizer, which number of layers, it is going to give you a highest accuracy. So that parameter you can directly use, and then you can build your neural network. That's the entire concept. Okay, that's the entire concept. How can you do regularization? How can you do a hyperparameter tuning? This is one of the way, guys. This is one of the grid search and random search to do hyperparameter tuning. There is also, which I told you, this is same as Keras. In Keras tuner also, it is going to do the same thing. It will try to take the range of the values. Okay, it will try to take the range of the values for the optimizer, range of the values for the loss function, range of the values for the dropout. Okay, so activation function and the number of neurons, all this combination value you have to pass. It will try to take one by one all the combination. It will try to run the neural network, and it will try to give you back the accuracy. Okay, so now you have to choose which accuracy you want, and then that parameter or combination of the parameter you can choose. Correct, guys? So hope now you are able to understand when people try to talk about this hyperparameter tuning. There are three options: grid search, random search, and hyperparameter tuner, Keras. Okay. All right, guys. Any doubts? Any questions as of now? Hope this was very detailed session. You are able to understand end-to-end background. No one, I'm sure, no one would have taught you this kind of a backgrounds. People try to teach you, but this kind of a background no one will try to talk about. All right. So guys, just last confirmation before we start the coding part. All right. So any doubts, any question as of now related to all the concept? Before we start coding the thing, we'll try to create our own architecture, and we'll try to pass the data, banking data, maybe with churn prediction, we'll try to calculate here. All right, guys, all of a sudden everyone is so quiet. Is it heavy session? Are you experiencing very difficulty in understanding this, or you are enjoying these complex sessions? Just share your thoughts. Or you are comfortable, or is it too much data load, too much download is happening? Okay, enjoying. Okay, Panushri ma'am, thank you. Agrawal sir, ma'am, thank you. Enjoying. Okay. Yeah, PPT you'll get. Don't worry, Murtuza ma'am, sir. Definitely you'll get PPTs. That's for you guys only. I've created these things. I will share with you guys only. Okay. All right. I'm getting kind of a mixed feeling now. Okay, going smoothly, waiting for hands-on. Okay, great. Thank you. Okay, guys. So let me stop sharing this one. Let's go back to the coding part now. Let's imagine how can we create our own architecture. All right. Then based on that architecture, we can start understanding this one. Okay. So let me share my screen. Just give me one moment, guys, and we can start talking about it. Okay. Just one moment. I'm opening my churn analysis notebook out here, and then we can go and discuss this one. Okay, right. I have many tabs open, so that's the reason. Just give me 1 minute, and then I can open this. Right. Okay, let's see page. Yeah. Okay, guys. I will talk loudly. I just wanted to open this thing. That's the reason. Let me share with you. Attendance you will get, guys. Yes. In 5 minutes. 5 to 7 minutes you'll get the attendance link. Okay, let me share now. Let me share my screen. All right, guys. So I have shared my screen. This is a Kaggle notebook, which you are able to see here. So let me know if you are able to see it correctly. So what we're going to do here, we're going to perform customer churn prediction using artificial neural network. Okay. So this is what we are planning to do now. So what is the data set we are looking at? Okay. Let's try to understand here. No, that we'll talking about right now, Bhanushri ma'am. Okay, we'll talk about number of hidden layer neurons and all. Okay, let's try to understand now. When we're trying to solve this case, let's imagine what data I'm trying to take here and what is that we're trying to solve here. Okay, so I'm trying to do a churn modeling. Churn modeling means I'm taking a banking customer data here, And on the basis of the banking customer data features, I'm going to decide whether this person is going to leave the bank in the near future or not. So if it leaves the bank, it will be like 1. If it is not going to leave, it will be 0, right? This is the indication we're trying to forecast in advance whether the customer is going to get lost or not. If we are going to lose the customer, maybe some kind of a customer engagement is required in order to retain the customer. And this is the banking data. Okay, let's try to understand what kind of a data set we have here. So in order to understand the data, if you try to look at the data, we have something called as row number here. We have a customer ID, surname, credit score, geography, gender, age, tenure. Now this tenure is tenure within the bank, like from how many years he is having association with the bank, right? So this is gender, geography means what location you belong, your credit score, surname, customer ID, row number. Okay. So there will be balance in an account. Okay. Number of products. So number of products means if you are having a home loan or credit card or some kind of a saving account or RD, fixed deposit, some kind of a interaction or insurance or something like that. So that will be called as one of the products. So how many products you have with the bank, and they have a special column whether you have a credit card or not, and whether you are an active member or not. Okay, and what is your estimated salary, and based on that they have corrected the data here. And now looking at this data, we have to train our artificial neural network so that it can predict in the future, upcoming 30 days, 60 days, and 90 days, who are my customer who might be going to leave the banks. And if I get to know, obviously I will be precautious and I will try to take the concern and reason how to ensure that these people are not moving. Okay, trying to getting engaged with them. Now look at the data and tell me, guys, which columns are features are important and which are not important. Looking at them, any few suggestions like which one you don't require in order to perform the prediction. Look at this and tell me very quickly. So we'll try to drop that columns and we'll try to consume the data inside it, and then maybe we'll go for it. Okay. All right. Balance. No, guys, we'll require balance. Attendance you'll get, guys. So Amar, Chandana, can you guys please share the attendance link? Everyone is asking for the same.
Yes, because I'm sharing that.
Yeah. Thank you. So guys, you will get the attendance link here. So these are important. Okay. Tenure is no, sir. Tenure is needed. Tenure, if you see tenure, will come to know. So maybe what will don't require is surname, because the surname of the person will not help you, right? So yeah, guys, geography, yes, could be possible, sir. We don't know actually. Credit score is also possible, ma'am. We require credit score because if person is having good credit score, maybe he's likely to stick to a bank if he's satisfied. Otherwise, he will leave, right? So if someone is getting low credit score, means he is probably tried to leave. Okay. So guys, Chandana has shared the link once again. Surname is not important, correct? Surname is not important. Customer ID will not help me, guys. Customer ID is not important. Surname not important. It will not help me to understand whether this person is going to leave. And this row number is unnecessary for me. Okay. So these 3 columns are not required. Credit score is required. Geography could be possible that like why geography is important. Let's try to understand. If we are living in Maharashtra, right? So if you are living in Maharashtra, mostly people what they try to prefer, they try to go to a local banks, right? So Bank of Maharashtra is there, some other local banks is there. People have a what you can say, they have a faith in the local banks rather than going from Bank of Rajasthan. The person who is living in the Maharashtra will try to prefer a Bank of Maharashtra rather than going for a Bank of Rajasthan. So that could be one of the reason. Okay, that could be multiple reason, that maybe he knows some of the people in the banking, right? So he's familiar with the bank people, so maybe he will try to get his work done very easily, right? So that could be multiple reasons could be possible. So that's the reason geography can play a very important role out here, right? When it comes to the sanction or kind of a documentation, obviously you know that if you're trying to talk the local language, they will help you out very easily. Otherwise there will be some issues, right, in the documentation and all. So that could be the reason, correct? So that's the reason. Customer ID, yes, correct, sir. Customer ID will try to remove. Customer ID, how do you process the data? Sir, we don't require customer ID. We'll try to first remove these customer IDs and we'll try to get the prediction. We can tie back these customer IDs to the particular row numbers. Okay. If we try to remove that, that is also possible. Okay. Gender could be play role or could not play role. That's also correct. So let's imagine this way. Okay. Let's now try to do this way. I'm trying to import the CSV file here. Okay. And as a data frame, then this is what I'm trying to see. I'm trying to describe the count in order to make sure that there is no missing values. We have a 10,000 records here. So everywhere in every column, I have a 10,000 records. So no missing values are there, right? So I'm trying to see the mean value and everything. The next thing which I'm trying to see here, what are my column types? Okay, data types, int is there, float is there. If I require anything, okay, products are important. Correct. Tellurians, manual product are important. Correct, guys. Okay, so I'm trying to check is there any null values present. So I'm using df dot is null sum. So there is no zero, there is zero null values, right? So that's good to go. Then I'm trying to separate my values, right? I'm trying to check my column, right? How many people are exited as versus to non-exited. So if you try to see here, there could be imbalance also. So my 80% data is not exited and 20% data is exited. So maybe this is not the balanced one. So you need to do a balancing, right? Before we try to build our model. That is one of the option. And how do you do the balancing is smart methodology is there. So sampling, minor sampling of the technique, up sampling and down sampling you can use. So make sure that there is a proportion in the output column, right? So if your model is heavily influenced by non-exited, it is a possibility that your model can also predict the similar way. So we need to have a balance of the class, right? So there are two classes. Smart, yeah, smart technology. You can read it, ma'am. Smart is this minority small, some name is there. I will give you that name, okay? Smart means they're trying to balance the class using kind of a sampling technology. So they will do up sampling or down sampling, means they will try to increase the sample or they try to decrease the samples. So just copy paste the more samples like this one. Whosoever people exited, just copy paste the same values again, and that could be one of the reasons where you can balance the class. Okay, once you balance the class, guys, now we are trying to check gender wise, geography wise, and the card has the card or not. So it kind of a feature selection technique we're trying to do, like here. So in geography wise, France, Spain, and Germany, these are three geographics. How are the customer trend exited versus non-exited? Then we're trying to look at the gender wise, who are the more people. So more female people are trying to not trying to exit, male are trying to exit. Okay, the bank tenure wise also, if you try to look at the tenure also, the people when you try to go for the tenures, okay, so that the more is the tenure, the people are not leaving the bank. This could be one of the reason. Number of products, if the people are having more number of products, maybe they will not leave the bank, and whosoever is leaving less product can leave. Active and non-active also. So this is the small kind of a we are trying to do a visualization. Obviously we're trying to do the box plot to understand is there any outliers or not, some kind of outliers present. I'll try to avoid the outliers. Then coming back to the question, right? So now I'm trying to do value counts, and obviously the next step for me was, so geography and the gender, these are two text column, right? So I try to convert them using the one-hot encoding, okay? Or I can simply do the mapping, okay? I can do mapping, I can do one-hot encoding. So here I'm trying to do mapping. Geography, map France to 0, Germany to 1, and Spain to 2, okay? Male and female 0 and 1. This is what I'm trying to do, and this is how my updated data looks like. So this is kind of a pre-processing we are trying to do out here, right? So once I am trying to do this kind of a pre-processing, guys, now my updated data look like this one. I have removed the customer ID, name, surname, and row IDs. I have a credit score, geography, gender, everything in the numerical. Everything looks good. Then next step will be either I can do a scaling or neural network can take care of the scaling also. Okay, so because some of the parts like salaries are very high magnitude and the balance are high magnitude, and the scales for the age and credit score are less, right? So there's a disbalance in the scoring also in the scale, right? So you have to take the decision. You can use the standard scaler and you can scale the data to the best ways to scale the data. Okay. Then once you scale the data, then you can drop the exited column, split the data X and Y. So X will be all your features, Y be your target columns now. Okay. And then split the data. Now we are trying to split in 75-25. 25% go in the testing and 75 go in the training. X train, Y train, test, 10 test split I'm using. Then I'm calling standard scalars here. By using the standard scalar, I'm trying to transform my data in the standards value 0, 1. And this is how my data will look like now. My all X has been scaled values now. Okay, so I have taken care of the scaling as well, because there are some high numerical values. There are some low numerical values in the parameters. Okay, features, sorry. All right, now how to build a neural network? Try to focus out here. So for building the neural network, we are going to use the Keras and the TensorFlow in the background. Okay, TensorFlow. So these are the two packages which we'll be using. TensorFlow will work as a background, guys, but high level API. Okay, high level API will be Keras now. So Keras is a high level API using which English language we can create our model. Guys, Chandana has shared the attendance link once again. So try to follow the link in the chat box. Okay, chat box is the same, guys. Comment box only, chat option. So these are the two packages we'll be using, guys. So you can see here Keras. Okay, so we'll have to import the Keras and the TensorFlow. You can use any version of TensorFlow, doesn't matter. Now import the Keras first, and from Keras now this is our model, guys, sequential. Okay, sequential is the name of the model. Now by using the sequential model, guys, we'll try to add the different layer. You can see here dropout layer. dense layer and the normalization. Dense layer means we are adding the layers now, the hidden layers, then input layer and the output layer. All these layers will be used using the dense layer. Dropout you already know for the regulation, and normalization also we can do in order to take care of the overfitting, batch normalization. Okay, so this is what I am importing first. So import Keras. From Keras model, use the sequential model. Then we are using layers for the layering purpose, dense layer, then dropout layer and the batch normalization layer. Now in first place, we'll directly not start with the dropout and normalization. Maybe you can use the normalization only. So try to hide the dropout first, try to create simple model first, and then maybe once you are able to build the model, check the accuracy and then try to add a dropout. So this could be a possibility. Okay, so first, once I imported all my packages, call my model equal to sequential. Okay, once you call this model, guys, then you have to add the layers now. So what layer I am adding? I am adding first input layer now. Okay, in input layer I am adding dense equal to 10. So model dot add dense. Dense layer means dense layer is used for add the, yeah, link is already shared, ma'am. Nandita ma'am, link is already shared by Chandana. You can follow the link. Okay, and she will keep on sharing the link once again. Yeah, guys, I'm not able to copy paste the link, otherwise I would have pasted the same link. Okay, so Chandana will share the link. So guys, first import the packages, then you import the model, and one by one we'll try to add. Now what kind of architecture we're trying to create here? This way. So I will add a hidden layer here. So sorry, input layer here first, then we'll have a hidden layer 1, we'll have a hidden layer 2, and then we'll have a output layer. Now coming to your question, now we'll try to talk about the question like how many neurons to be included, how many layers to be included, what kind of a function to be included. Okay, and how many output neuron should be there in the new output layer. Okay, that's the question we are trying to talk about here. So this is the model sequential, then we'll try to add one layer each. Okay, so the two layers will be there. Let me show you the model architecture below, then I'll show you how to train the model. Okay, so if we try to take the model architecture here, so this is what the model architecture look like. Okay, so model name is sequential. It is very simple, model.summary, and by using the model.summary, guys, you will be able to see the architecture. Now if you try to see the architecture, guys, just avoid as of now layer. So this is layer, this is dropout. Now look at the parameters. Okay, so by using these parameters, when dense layer I am adding, and first dense layer, this is my input layer. Okay, in the input layer I am adding like 1 1 1 1 to 10. So I'm adding 10 neurons here. Then I have something called as hidden layer here. So as of now, forget this one. So this one also batch normalization, forget this one. So this is my hidden layer 1. Okay, in hidden layer I'm adding 7 neurons. Okay, so this forget this one also, drop out now, normalization. So this one is my second hidden 2, this is hidden 1, and this is my input layer. Okay, in input layer, if you see the number of neurons 10, this is 7. Again I am taking to take 2 neurons here. Okay, dense layer 2, hidden neuron 2, and then there will be my final output, which will be I am taking 1 here. Okay, 7 2 and the 1. This is what the I have taken, and let me show you here. Okay, so this is my last layer where I'm taking 2 or 1, we can say. Okay, so now guys, this is what the architecture, and you can see this architecture by using something called as model.summary. Okay, by using the summary you will be able to. Yeah. So Satya, this is what we are trying to do, Satya sir, ma'am. Yeah, we are trying to teach the coding here already, right? How to do the coding part now. And now here activation function, I'll tell you how to do. Right now the question before we go into this thing. So my first question is how many neurons I should take in the input layer, right? Input layer. So can anyone tell me, like here I'm taking 10. So what could be the reason I'm taking 10 here? What could be reason? Anyone can tell me? What could be the reason I'm trying to take 10 neurons here? Why not 20, 30, 40? Number of feature. Awesome, Banushri ma'am. Awesome. Okay. So number of feature in the data set. Correct. So guys, the logic goes behind the input layer is 10 columns. Correct, sir. So if you have whatever number of columns or whatever number of features you are having, take minimum that many, right? So whatever the features you are trying to input here, so if you have input from x1 to x10, at least you should have that many neurons present right here in order to accommodate that information. That's the reason we simply try to take 10. Now coming back to the hidden layer, guys, hidden layer you can take as per whatever you wish. Okay, you can take 10, you can take 17, you can take 20 as well, doesn't matter, doesn't matter. Then it will come the output layer, then comes the output layer, and within the input layer, within the hidden layer, guys, within the hidden layer we'll take the activation function as well. In the coding part I will explain you. This is the summary part. As of now we are trying to talk about, first we'll fix the architecture, then we'll try to add that many layers, and then maybe we'll think of adding normalization and dropout layer inside that. Okay, based on the calculation, based on the accuracy levels. So let's try to understand here. So last logics remaining is now hidden layer, there is no such thing. Hidden layer you can take 1 to 10 or n, doesn't matter. But now you know that if you try to go deeper, right, if you try to go deeper, then you will be facing vanishing problem, exploding problem, and there could be some issues also. So try to take optimized layer. As of now we'll try to keep 1 or 2 layers as of now, right? So I want to utilize, or I want to check by using 2 layer whether I'm able to achieve my entire architecture or not, right? Whether am I able to fulfill my objective or not. Okay, now the question comes, last question remaining out here is how many neurons I should take inside my output layer. Any logics, guys? Any logics? Any ideas that how many neurons I'll be taking in the output layer? 1. Any logic? Why 1? Number of classes. Awesome. Correct, guys. So in output layer, I'm taking only 1 neuron as of now, but because I am doing binary class classification. I'm doing binary class. Either my output will be 1 or 0, whether person going to churn or not churn, right? So 1 neuron is more than enough for me. Okay, and now based on my classification, correct, based on classification, if I'm trying to predict the number of digits, the digits are from 0 to 9, so maybe at that time I will take then 10 neurons, because I need to know the probability for each and everything. Okay, as of now I just need to know the probability, and this is binary class classification. So for binary class we'll be taking something called as sigmoid function here, and for the other class we can take, yeah guys, Chandana will be sharing the feedback link. Okay, now the architecture is fixed, this is what decided. Now let's keep on adding these things. Now then we can add these things and then create our architecture. Okay, so I scaled my data, I've taken my model here. All right, hidden layer neuron now depends, guys, now depends, it's a kind of a plug and play, trial and error. Okay, now you can take any number of neurons possible, but try to keep a proportion. And epochs, yeah, epochs logic is, guys, try to keep very less epochs as of now, right? Try to keep like 5-10 epochs and try to check the accuracy. Now again it is a hyper parameter, right? Epochs and the neurons. Now it depends on the trial and error, but the logic is, the logic will be like this way, guys. So whatever the neuron you struggle with the shape mismatch previously. Okay, now you are clear. Okay, so shape mismatch will only happen, guys, when you are not trying to take the proportion to the inputs and the outputs. Otherwise in hidden layer you can take anything, it will not stop you from that. Okay, so because I've seen that, or you can directly take the transfer learning model also and try to refer that. You try to create the similar model, so it will be possible. Okay, so just a moment, guys. So let's go back and try to understand here. Okay, you placed output layer has 2 neurons. Okay, guys, that we'll try to rectify it just for the simplicity purpose, but we in reality will try to keep it 1 only. Okay, we'll try to keep it 1 here. Here it should be 1. Okay, so guys, let's try to add. Now first you call your model, you imported all your layers and model, then call your model equal to sequential, and then add first input layer. I am always using activation function ReLU. The input shape I am taking 10, because you need to first, only in the input layer only you have to tell the input dimensions. So my input dimension will be 10, right? So this is what I'm writing. Yeah, we'll get the class recording on the LMS, ma'am. Sir, you'll get the class recording LMS. You can see, and it is available on YouTube as well. Okay, you can get the link, follow the link, you'll get the links. Kernel initializer purpose. Kernel will play a role in the say, try to understand kernel initializer is playing a role, means whatever the filters we are trying to apply here, at that time we need to initialize these kernels, right? So here even you can take the kernel initializer or you can drop it for the simplicity purpose. But when we're trying to deal with the convolution neural network, at that time kernel initializer is very important. Okay, so we need to initialize the kernels. Kernel initializer means how we are trying to take the filter out the data. That's the reason kernel initializers are there. Okay, as of now you can forget it. Kernel initializer, try to keep it normal. Then I'll explain you in the convolution neural network what the kernel initializer will play a role. Okay, as of now just try to add here dense layer, then activation function and the input dimension. Okay, so kernel initializer as of now try to understand is one of the parameter. We'll try to keep it normal only. We don't want to go into the complexity as of now. And then mention the number of neurons you want. Okay, model.add you can drop out this also, guys. Okay, you can drop out this parameter, so it will not make any sense also. As of now just you need number of neurons here. Then activation function, I'm taking ReLU. I don't want to create a kind of a vanishing problem, so that's the reason we are taking ReLU. Then take the input dimension, only one in input layer only you have to take the dimension, otherwise you don't need a dimension. Now it is not mandatory. You can later on, as of now keep it, hash it. You can add these layers later on. First try to create a vanilla flavor. So this is the first thing, model.add number of neurons 10, then the activation function ReLU input dimension. Then the second one, dense layer 7 neurons, then activation function again ReLU. Okay, and then try to hash them as of now, and then we'll try to rerun again model with the making them okay active. Batch normalization will help you to normalize the data. Okay, what will happen after doing or passing this information, right? So after passing that information, batch normalization helps you to control, or it is kind of a way how you can do the regularization in order to avoid the overfitting. That's the reason try to do batch normalization. There is a batch normalization across the depth and across the layers also. There are certain other things. So you can use class normalization, batch normalization also, but batch normalization is better to avoid the overfitting. Okay, that's the reason in order to control the or do the regulation, they are using these two techniques, dropout and batch normalization as of now. So first try to run without activating them, try to hash them. First add the simple neuron, then add the hidden layer. Okay, so hidden, and then the last layer, this one, this is the last layer, try to keep it 1 as of now. Okay, so don't take it 2, this try to keep it 1. Okay, and then once you take it 1, our entire layers are ready. Then we need to compile our model. Okay, so model.compile. Now here the optimizer is your choice now. So just performing better, you can use stochastic gradient descent with momentum, or you can use Adam also. Then what kind of a loss function? Since we are doing binary class classification, you are using binary cross entropy. Otherwise you can use sparse cross entropy. It is a multi-class classification. Okay, matrix accuracy obviously. And then guys, once you add this, then you can say model.fit. Then you pass your training data. Then validation split, we already know. You can do 80-20, you can do 75-25 as per your, okay. Yeah, we'll show the model accuracy. And then validation data. And then epochs, I'm taking 100. You can keep 10 as of now. Okay, so don't go for 100 as of now, because these people have run it for multiple one. So keep 10. I will give you one more example also tomorrow, where I'm just within the 10 epochs also I'm able to achieve the same accuracy. Okay, so this is trial and error. Don't go for higher epochs as of now. Go for 10, 20 epochs. Okay, that's how you'll fit your model. Model.compile, model.fit, and your entire training will start, guys. Okay, so epoch by epoch. Now you try to see here. When you try to start with the epoch number 1, you can check the loss is at 65, and your training accuracy, okay, and test accuracy 79. So model epoch by epoch, when you try to go down and we to try to finish this validation. Okay, so in the end you can see the model accuracy is at 86. Okay, so 84 is the training, and the testing is 86. Okay, so these are close. There is not a huge difference. Now we can plot this also, number of epochs and the loss. Okay, so model.history we have a loss, model.history we have a validation loss. This loss is training loss, and this is a test loss. And then we are trying to plot the number of epochs as well. So this is very simple by using plt.figure or plt.plot. Then you can use this one and you can plot the figures. Okay, so plt title label we are showing and plt.show. Now you can see here, these are the number of epochs starting from 0 to 100, and this blue color one says the training loss and that validation loss. So since we already applied here, guys, we already applied the drop on regulation. That's the reason you are not able to see the huge difference. Otherwise, first what will happen is your training loss will be like this one only, and your testing loss, there will be difference. Okay, actually. So when the moment if you try to see, there is a difference. Now this is pretty smooth graph. Both are very close to each other. That means there is no overfitting. Okay, overfitting is not there. Why? Because we already run with the dropout. So try to run without the dropout layer, and then once you try to run with, so maybe you will try to experience the graphs in this way, right? So there will be difference between these graphs. Okay, this one, this will be the one, this will be. So you'll see some differences. This difference means it is trying to overfit, because validation accuracy and test accuracy, there is a huge difference. Okay, so because of this difference, then if you try to experience this difference, then obviously you come back, and then maybe you simply have to add in between. Simply had to add what you have to add, then the dropout. Okay, and you can also decide this parameter of the dropout also. So whatever the dropout and regulation we have added here, we are taking 10% dropout and batch normalization. You can go with 10%, 2%, 1%, as whatever you want. Okay, so 2 times we have added here batch normalization after every dense layer. After every dense layer. So sequential is the popular model if you want to go for Keras, and if you want to go for the other one, there is a PyTorch model. Okay, so which we can use. The name of the PyTorch model is something else, so it is like a class and all. Okay, so but for most special, even if you go for the convolution or recurrent neural network, they are using the same sequential model only. So there could be some other models as well, but the popular model is sequential, guys, only. Okay, so then first you run with this one, and then you try to add these 2 layers. Okay, drop on, and then try to check the accuracy as well. So here we have run, guys, 2 times this same model, and you can check out by using this. Okay, plt dot model, plt plot underscore model. Okay, this is one of the function in the Keras utility function. Plot the model, and you can pass your model, sequential model. It will give you a graphical overview also. So how your dense layer, how is this input layer, dropout layer, how it is working, entire graphs also you can see it here. Okay, so this is one way, guys. Tomorrow I will try to showcase you also. So how can you, okay? Not compulsory, sir, ma'am. Not compulsory. Now that's the reason I told you that. That's the reason. Okay, that's the reason I told you that. First, don't add even this one. Okay, batch normalization dropout. So don't draw. Actually, I am missing that code with me, where I usually don't. I'm not adding this in first place. Then first I try to run without adding these layers. Okay, just hash them. Just remove them also, it is possible. Okay, just remove them and then try to run, and then try to check this accuracy, then try to plot this accuracy. If your accuracies are different, then you can add it back and then check it. Okay, so these are for the purpose to control your regularization. Okay, control your regularization. You can check here after the validation and epoch also, you can check like how the accuracy look like, right? Accuracy started with 72 and then it went ahead. So here we are plotting accuracy, and here we are plotting our loss function epoch by epoch. Okay, both the graphs are available, guys. I will share this code also with you, this model, for your reference. Tomorrow, guys, what we'll try to do is, tomorrow now we have passed here the structured data, correct? So here I have passed the normal structured data, right? So here I passed the banking data. Okay, this banking data, this is the structured data. Tomorrow I am going to take the same neural network, but here I am going to pass the graphical data, Aminis data set. The data set look like this one. So what we'll do is we'll at least take the 10,000 images. Okay, 10,000 images for these numbers written, handwritten numbers. Okay, and then we'll try to pass this to the same neural networks here. We'll try to pass the same thing to the neural network only, artificial neural network. You can see here the flattened layer, dense layer, dense layer, dense layer. Here I am taking 2 hidden layers, 1 output layer, and this simple model is there. Okay, without any regulation, without anything, without any dropout I've taken here. Guys, you can watch the recording. If you miss the class, you can watch the recordings as well, right? So tomorrow what we'll try to do is we'll pass a image data here. Okay, like this one, we'll pass the image data which will have a 0 to 9 numbers written on it, and we'll try to pass 10,000 images, and then we'll try to check how the neural network is able to handle this image data, and we'll try to run them for these many epochs, guys. Okay, this is epochs, this is the architecture, model architecture. Okay, and then we'll try to run them, and we'll try to see here. If you see here, just to showcase you. Okay, so here in the model architecture, I have not added any dropout, any normalization. Okay, I simply run my model, and now if you try to look at the model loss function, okay, there is a huge gap. See here, this is the training, this is the validation, this is a huge gap. How much is the gap, guys? If you try to see here, the loss gap. Okay, so this loss gap is almost around 10% gap. Okay, so that's how you should be able to find out first. So this gap should not be there. If there is a gap, means your model is trying to do overfitting, because whatever the accuracy is there in the training and testing, there is a 10% difference. So that's how once you are able to confirm, okay, this is what is happening, and this is the difference also. If you try see here, it is 97%, it is 99, means accuracy is okay, but the loss is having huge difference. Okay, so that's the reason. Then you can add, come back here, then you can simply add one line code, model dot add dropout, model dot add the batch normalization layer, like this one. Okay, simply just copy paste this kind of a thing. Okay, these two things just copy here and try to add it here, then we'll try to explain, okay, how the things will work. Okay, all right guys, so this is what we'll try to go into the details. We'll see that how the artificial neural network can handle this data, and we'll try to focus tomorrow on convolution neural network as well. I'll give you a glimpse, and maybe tomorrow I will try to teach you. Are you guys able to see this Keras tuner, guys? Keras tuner, this one, optimized CNN model. Can you guys tell me? I have shared my entire window, I guess, with you. So you should be able to see my different notebooks. Correct? Just quickly confirmation anyone can give me. Are you able to see this one? Create CNN model after tuner. Yeah. So this Keras tuner also I will talk about tomorrow. Okay, this Keras tuner will help you to do the fine tuning of the data set here. Okay, this is how we'll try to build, and we'll try to pass out the different values for the tuner, and we'll try to see trial and error. Okay. All right, guys. So hope you enjoyed today's session. So we've seen the practical wise. We'll try to deal with the image data, and then we'll try to create this CNN model with the Keras tuner also. I'll give you small glimpse about the convolution neural network, how they works upon, and then we'll try to learn this coding as well, Keras tuner. Okay, we already know the grid search and random search is also there. Yeah, guys, Satya sir, Reshma, ma'am, thank you. You'll get the attendance link. We are pasting it here in the chat box again, okay, for your reference. All right, guys. So any questions, any doubts as of now on this one? Whatever things we have learned here. We still got 2-3 minutes, so I can answer a couple of questions and we can close the session for the day. Banushri ma'am, see, if every 5 columns are grouped as one channel out of 10 columns, I mean 62 groups, then can we pass 5 columns to one neuron, and then and we take 62 neurons in that? I have not tried this, but you tried. You can try this one. You can try this one. Or what people do is, like, they try not trying to group the things. They're trying to pass in the batches, guys. Okay. So they try to instead of doing grouping, you can pass in the batches. Okay. You can pass in the batches, and you can look for this one data. All right. Try to pass in the batches data. Kernel, we'll talk tomorrow. Kernel will talk to. Yeah, you can batch, ma'am. That's what it's saying. Rather than passing in the single flow, you can pass in the batches. Number of batches. Here there will be like batch size will be there in model.compile. This is Python only, ma'am. This is in Python only. This entire code is in Python. All the codes which I'm talking about is Python only. Satya, ma'am, sir. Yeah. Hope guys you enjoyed today's session. I know it was a bit critical and complex when it comes to mathematics and all, and then chain rule and all. What use dropout in input layer? Not in input layer. We'll use after input layer. Input layer, if you try to use, then there will be less. You can say input will be going inside. So that means neurons will be getting deactivated, right? So in hidden layer maybe batch size for sample, right? Yeah, batch size for sample. Correct. Batch size for samples. That's what we are talking about. There will be one simple parameters here. When you try to compile the model, I will show you also possible. So you can use the batch size as well here. Okay. Batch size, and then how you can fit. Columns means ma'am, for every okay, in the example explain used it. Okay. Okay, in example can explain you used it in PPT. Okay, I will explain tomorrow. I will explain this one. Batch size affect the result? No, it will not affect the result. It will not affect. Only thing is, and batch sizes, if you're trying to take it, and for columns, I will tell you in the columns how you can accommodate. Now I understood. In batch sizes, we are taking samples, and how can you accommodate the columns at a time? I will also explain you, ma'am. Okay. No, it will not affect most probably. The batch size should not affect, okay? Because batch size, what is the logic of the batch size? Because you cannot accommodate all the data at the same time, right? That's the reason. Input, okay, input in the drop. Yeah, guys, it is not mandatory. See, what I'm saying is, so if you're trying to say here I am use the dropout, right? After just immediately after this one, right? That's the reason I am saying it that don't use that as of now. Just for the simplicity I have added here. Just don't use it directly after this one, okay? Use it maybe directly after this one, and then after this dense layer. That's what I'm saying. Just cut this one. Just cut this one. Possible. Okay. No, sir. That Rajashri ma'am, sir, when you train your model, okay, your model is trained, then you don't have to train once again. Yeah, I'm on LinkedIn. I'm on LinkedIn. Yes, guys, you can search me. You don't have to train again and again. You can use the same trained model. You'll understand. I'll show you some pre-trained models. Okay, pre-trained models are that. That's what is called as transfer learning. Okay. Yeah, Banushri ma'am. Thank you. Yeah, that's how I learn. Okay. Okay. Thank you, ma'am. Rajeshri. Yeah, same. You can search by Vikas Narune. You can search by Vikas Narune and you can search me there. All right. Yeah. Thank you, Madhuri ma'am. Thank you, Madhuri Sahu. Rajeshri ma'am. Thank you, Fatik Kunwar. Thank you. All right, guys. Then would like to close the session for the day. Tomorrow we'll try to focus on these two things. One is image data set and then Keras tuner, and we'll try to have a glimpse of the convolution neural network. And then day after tomorrow, Friday, we'll try to talk about ChatGPT and RNN. All right, that's the agenda. All right, guys, then thank you very much. Thank you for your kind words and for thank you for the participant and engagement. You guys are really awesome. Very, very pro guys. So I really enjoy taking these sessions. And then see you tomorrow then, guys. If I have any other question related to the attendance and all, you can talk to Amar or Chandana. All right.
Yes, because I will take it up. Okay.
Okay, guys. Thank you very much. Then I will leave the meeting and see you tomorrow then.
Yeah. Thank you so much.
Yeah.
So, any more questions for me? Let me know in the chat box. I'll try to address it, or else we'll wind up the session. Day two feedback. We can't able to share it, ma'am. I hope there is no more questions. So we'll wind up for the day. Please share on the group. Yes, I'm sharing the WhatsApp link. Are there any certification? Yes, for this, we have a certification also. For the certification, 60% attendance is mandatory. Oh. Yeah, I'm sending the attendance link. So after that, you can. So Narendra sir, it's a Vikas Narune. Okay. So we'll wind up the session for today.